Um, so this was kind of a national story for a while, maybe even an international story, as the city with the worst pollution in the world for this particular day was New York City. And people are typically accustomed to relatively clean air in that part of the world. And so this was a bit of a wake-up call that due to, in this case, due to climate change, these wildfires were raging longer and over a bigger area and causing this extreme pollution problem. So you can go to the next slide. So this is just my 15 minutes of fame. I was on CNN. That's me talking to Jake Tapper about the air pollution problem. So I just had to put that up there as well. It became a major story in all media in the U.S. and even there were some international orgs as well that were interested. So next slide. So let's talk a little bit about the composition of particles. This is a map here showing, it's kind of hard to see, but the pie charts are showing different chemical compounds that make up the particles. And you can see that it's very different but based on where you are. So if you're in the, let's say you're in Eastern Asia, you're somewhere in China, the biggest source of pollution or the biggest contributor to pollution is typically sulfate aerosol, sulfur particles. And what does this come from? Well, it mostly comes from coal-fired burning, coal power plants, all right? Large electricity generating units that exist in China to be able to provide electricity to a very large population. You compare that to Central Africa here. So the bottom pie chart in the middle, you have this big green sort of slice of the pie. And that's actually representing organic aerosol. So a totally different chemical composition. And that's, for the most part in Africa, there's not as many of these sort of legacy power plants that are burning coal that we've seen in China and in Europe and in the United States and Canada. So because of that, you have a much different type of a much different chemical composition. And these different compositions have different health effects, and we don't really fully understand that yet. All right, so a sulfate particle versus an organic particle will impact human health differently. It'll impact climate change differently. It'll cause all kinds of different problems. And so the issue is very, very complex because we need to be able to know what the composition of the particles are. And we don't always, in many places of the world, we don't have that. Next slide. You can skip this one because I already talked about this. So I just want to talk briefly about ground level ozone. All right. So ozone at the surface, the bad ozone. It also is what we would call a secondary pollutant. There's no such thing as ozone being emitted directly from the surface. It also requires some complex chemical reactions to form. So you have things like nitrogen dioxide emissions that come from vehicles and power plants. And then you have volatile organic compounds, which I mentioned. Some of those come from trees, from vegetation, but also there's a lot of human sources of those. Those two things mix in the atmosphere, and they also undergo some photochemistry, which means that it takes sunlight and energy from the sun to initiate the chemistry. And you mix all that together and you eventually form ozone. Next slide. Yeah, so this is just sort of a schematic showing, you have in any part of the world, you might have some cities, you might have some forests. All of these VOCs from the forests can mix with the VOCs and the nitrogen dioxides from the cities and create this sort of complex mixture, which then with sunlight will eventually form ozone. Next slide. And so this is going to be just some deep dive into some chemistry here in my last few slides. And basically, in order to form ozone, the oxygen atom has to be split. All right, so you can see this picture here. You have this oxygen molecule. This oxygen molecule has to be split in order to form ozone. Just only using that reaction, you can't form enough ozone that matches what we see in the atmosphere. So clearly there has to be something else going on. It's more than just a photon splitting the oxygen molecule into two oxygen atoms. So go to the next slide. And so what happens is an air pollutant, nitrogen dioxide, can also be split by sunlight. All right, so this NO2 can interact with a photon energy from the sun and break up. It can break up into NO and then a single oxygen atom. All right, and so that is the source of these oxygen atoms that then recombine with molecular oxygen to form ozone. All right, so you can see the net reaction there. Molecular oxygen is abundant in the atmosphere. The atmosphere is 20% molecular oxygen because that's what we breathe. That's what we, that's how we survive. So whenever there's these single oxygen atoms that get broken up from nitrogen dioxide, they can quickly combine with the abundant amount of oxygen molecules out there to form ozone. However, if we go to the next slide, that actually doesn't explain the whole story still, unfortunately, because the nitrogen dioxide reaction forms some ozone, but it doesn't form enough. It doesn't form enough to explain the observations that we see. So we can observe how much ozone is out there, and we try to figure out what is driving that. And the NO2 alone doesn't do that. So there has to be one other thing, and that's where the VOCs come in, the volatile organic compounds. And so these VOCs provide a source that can basically add more NO2, all right? So if you go to the next slide. The VOCs or the hydrocarbons are oxidized in the atmosphere, and they form what are called peroxy radicals, which then form NO2. And then that NO2 goes and forms ozone. All right, so let's just set aside all this chemistry for a moment. That was a really fast overview of some pretty complex chemistry. So I don't expect you to, if it's new to you, I don't expect you to fully understand all of it. The take-home message is you need 3 components for ozone to form in the atmosphere: volatile organic compounds, nitrogen oxides, and sunlight. All right, and so the nitrogen oxides are almost entirely from human activity. The VOCs are from a mix of human activity and also vegetation. And the sunlight, that's obviously from the sun. I think that's my last slide. Let's see. Next slide. Yeah. So I'll just leave my summary up here and take a few questions if we have time, and then we'll take a quick break. Thank you. So we have some mics that can be passed around if anyone has questions.
Thank you very much for the presentation. I was looking for some explanation of the term ocean fertilization.
Yeah, thanks for that. So that's another reason to care about air pollution. In particular, there's some air pollutants that can dissolve in water. And in fact, a good example of that is dust particles. So dust particles contain iron because iron is in the surface of the earth. And some of those dust particles, when they eventually come out of the atmosphere, how do they come out of the atmosphere? It's either by rain or by just gravity. And some of that, since the Earth's surface is 70% ocean, some of those dust particles are going to hit the ocean. All right. They're going to fall into the ocean. And so if those particles contain iron, they're going to essentially fertilize the ocean. And what I mean by that is provide nutrients that cause certain types of organisms to thrive and to grow and to, in some cases, grow to a level that becomes harmful for other parts of the ocean. All right. So ocean fertilization, iron particles deposit into the water, and there are certain plankton and certain not vegetation, but certain photosynthetic organisms that live in the water, mostly like plankton and stuff like that, that thrive with additional iron. And so that iron, they can use that to basically metabolize, to eat and grow. And then suddenly you have an ocean area with massive amounts of plankton. And that's not always a good thing, because then that consumes some of the oxygen. It's bad for a fish. It's bad for any of the sea creatures. There's also some, climate related aspects as well. So yeah, that's ocean fertilization. Steve has a question.
Thank you very much. I'd like you to throw a little bit light on how the types of plants and how they produce VOCs. You made mention that I had a perception that every plant was good for the environment, but now you just said that it's not exactly so. I'd like you to throw light on the types of plants and how they affect the environment. Thank you.
Yeah. So let me just first say that in terms of taking up carbon dioxide, trees are definitely a good thing. They do that very well. Let me give you an example. Maybe this won't work too well in Africa, but pine trees. If you've ever been in a forest that has pine trees, I know that those type of trees are not common in this part of the world, so maybe it doesn't work too well. But pine trees they grow in sort of the boreal forests of the world. So kind of Canada, Scandinavia, Siberia, northern part of the world. And there's this sort of distinct smell that you can smell from pine trees. It's what we just call a pine smell. What you're smelling is VOCs, volatile organic compounds that come off of those trees as part of their normal life cycle. And so it just turns out that those VOCs are really important precursors to forming air pollutants like ozone and fine particles. All right, so they don't necessarily add particles or ozone themselves, but they add an ingredient that can then undergo chemistry. And so in terms of air pollution, trees are not necessarily always going to help. All right. So if you see kind of people saying, oh, to reduce air pollution, we planted trees. Well, that's true for carbon dioxide. That's true for CO2. It's not really true for a lot of other things. So it's just an important distinction. Thanks for that question.
Hello.
Yeah.
Thank you. You talked about ozone in the troposphere, and I think you did mention that it has impact on plants' growth. Maybe just throw some small science on that for me. I like some understanding there.